Welcome everybody to our last session on machine learning attacks. And in this session, we have 4 wonderful papers. So the first paper will be transpose attack, stealing datasets with bidirectional training. And the authors Guy Ahmed from the Ben Gurion University. He's an PhD student candidate and also an AI privacy researcher from IBM research. So if you are ready, you can go and test the slides. You can test the button. I think yeah. Okay, cool. So let's give the speaker a warm welcome.
But can you turn this projector a little bit down? I'm completely blinded. Projector is completely blinding me. Okay. Okay, anyway, I will begin. Okay, so I'm very excited to be here. My name is Guy Ahmed. I'm from the Offensive AI Lab at the Ben Gurion University, and I'm here to present our work, the Transpose attack, an attack for stealing datasets from secure training environments. Before I begin, I would like to say a few words about our funding. This research received funding from the Horizon 2020 research project called Chameleon. In Chameleon, we develop an online repository which facilitates the training of deep learning models on confidential medical datasets. Okay, speaking of datasets, the value of datasets in the eyes of attackers only increases as deep learning scales. And the reason for that is that serves in 2 main reasons. One is the fact that developing a dataset is very expensive, thus selling it will result in high profits. And the second reason is that the dataset may hold private and proprietary information, which may be of use to some potential adversaries. Now, the threat that we are here to discuss today is the threat of letting others train a model on our datasets. In previous research, it was already shown that when a deep learning model is trained on a dataset, it memorizes part of it. But with the Transpose model, we are going to show that this threat gets much worse, and he managed to force a model to memorize a large part of a dataset, and then this data can be systematically extracted. The threat model we are working with this paper is a threat model for a secure training environment, and in which we assume the following things. 1, the attacker cannot export the training data out of the environment. 2, the attacker can only access the model after it is being exported out of the environment. 3, the attacker may modify the training code. 4, all models are actually subjected to an auditing process before they are exported out of the environment, meaning that they are checked for legitimate architecture and reasonable performance. This is to ensure that a zip file containing all the data is not actually masked as a model and exported out of the environment. In the scope of the paper, we've identified 3 scenarios in which our attack is applicable. The first one, which is our main attack scenario, is federated learning. In federated learning, several partners collaborate in order to train a deep learning model. The partners designate an orchestrator to manage the process. If the orchestrator is either malicious and wants to steal the partner's data or has been compromised by a third party, our attack can be used to steal all the partner's data. The second scenario is a cyber attack, such as a supply chain attack, in which an attacker infects the code of a popular training library such as Hugging Face, and then casually awaits for this model to be embedded inside the software. Then, the attacker gets his hands on the software and extracts all the data from the model. And the last scenario is a data and training as a service platform, which allows training deep learning models on confidential datasets, which is a kind of common thing in the healthcare industry. Throughout our work, we've identified two common and two related topics to our research. The first one is multitask learning. In multitask learning, a deep learning model is trained for more than one task. For example, an encoder-decoder model with two decoder heads. One decoder head can be used for the legitimate task of segmentation, while the second and the other hand can be used to recreate all the training data. The problem with this approach is that in order to recreate the training data, all the input encodings have to be saved alongside the model, which does not fit our threat model. The second scenario is stenography. Using stenography, data can be hidden inside various other data types. For example, in neural networks, compressed datasets can be hidden inside the neural network weights. However, this approach does not fit our threat model as well, because it is actually very vulnerable to simple prevention mechanisms, such as scattering a low magnitude of noise on the neural network weights, which completely deletes the embedded data. So our research is here to fill the gap of being a method for producing a benign-looking model which can secretly perform the task of data extraction in a robust manner. So how do we do it? We use what we call a transpose model. The transpose model is a model that can perform two tasks at the same time. One, a cover task, such as classifying medical images, and a hidden task, such as memorizing medical images. Now, what is special about the transpose model is that the hidden task is actually executed through the transpose of the model. What do I mean by that? Well, I mean that the model is actually executed in reverse. Let's take a look at the VGG19 network. Usually, it processes input images by passing them through a series of convolutional layers, and then through a series of fully connected layers. In its transpose operation, the VGG19 processes an input query E using first the series of fully connected layers in their transpose operation, followed by the transpose operation for the convolutional layers. So what is this transpose operation? Well, it is as simple as it sounds, but it literally means transposing the layer weights. For example, for a fully connected layer F, parameterized by weight matrix A, executed as sigma of A times X, the transpose operation will be sigma of A transposed times the input query E. So for the transpose model to work, what we need to do is train it and learn a shared set of weights, theta, that will fit both executions of the model, meaning transposed and forward. Now, in general, the transpose model can be used to perform any arbitrary task. But in this paper, we focus on data extraction. So thus, we propose the task of memorization. Memorization is a task for retrieving images from the datasets and make the model answer queries of the form, give me the ith sample from class C. How can this be done? Well, we use what we call a spatial index. A spatial index is a unique identifier for each sample the attacker wishes to memorize inside the model, and is the input for the transpose direction of the model. It is implemented using multi-dimensional representation of gray M code, as can be seen on the image on the right, and classes indicators implemented as one-hot encodings. The idea is pretty simple. Each class's samples are enumerated using the gray M code, and then this representation is separated according to the classes using the classes indicators. Let's take a look at how it looks like. In the middle graph, we see gray N representations for all the samples in the dataset. On the left, on the right, we see the directions of the one-hot encodings. When we put them together, we get the representation on the left. We see that each class's samples are actually separated, and the distance between each two following points in gray code is separated by exactly one distance unit, which facilitates the training of the model. And what is special about this representation, it is that it does not have to be saved alongside the neural network weights, meaning that it exactly fits our threat model. Now, let's put this together. We need to train the transpose model for two objectives simultaneously. For that, we use separate gradient steps, one for the transpose direction and one for the forward direction. In each training iteration, we first train the model for the forward direction using a benign task, such as classifying images. Then, we transpose all the network weights and draw a batch of spatial indexes and their corresponding images for memorization. We then perform a separate optimization step to improve memorization and transpose back all the layers and repeat this process until both tasks converges. In the evaluation of our paper, we examine three aspects. One, the memorization capacity of the transpose model. Two, what is the effect of the model size? And three, our ability to perform IP theft using the extracted images, meaning how usable the extracted images really are. In front of you is a figure illustrating what happens to the sample's quality when we memorize more and more samples. On the left, we see images from the MNIST, CFAR, and Celeb-A datasets. In each following column, we see what happens to the quality when we memorize more and more samples. We can see that even when we memorize the complete MNIST dataset, the digit 5 is still completely identifiable, and even when we memorize 21,000 images from the Celeb-A dataset, we can still definitely identify the person in the image, meaning that using our attack, we can perform explicit membership inference. As for the model size, we have identified that in general, models with few wide layers are actually better at memorization than models with a lot of layers, but in an unsurprising manner, with more trainable parameters, we get better memorization. For our last evaluation, we wanted to check how usable the extracted samples really are. For that, we performed the following process. We draw a sample of images from the dataset and train on them a regular model. Then, we use the exact same images and train on them a transpose model for memorization. We extract the images from the model and train on them a second model with the exact same architecture as the first one. For the evaluation, we compare the respective accuracies. We can see that when we memorize half of the MNIST dataset, we get an accuracy drop of only 0.2%, and in a similar manner, when we memorize 21,000 images from the Celeb-A dataset using a vision transformer model, we get a performance drop of only 1%, meaning that the extracted images are fully usable and can be used instead of the original ones. This is an actual IP theft. In the scope of the paper, we also discuss a detection mechanism. It is based on a very simple hypothesis. A model that was not trained as a transpose model should not be able to generate realistic image content through its transpose operation. To check that, we use a process similar to the creation of adversarial samples. What we do is force the model to output an image similar to one image from the dataset, and if the outputted image is indeed similar to an image from the dataset, then we know that the model is infected with the transpose attack. And if not, then it's not. We share more details about how this detection method in our paper. And in summary, this paper proposes 3 novel contributions. 1, the transpose attack vulnerability, which allows the training of secondary functions inside neural networks. 2, the novel task of memorization, which allows the systematic extraction of training data from our transpose models. And 3, a detection strategy allowing the detection of models infected with the transpose attack. That was it. That was the transpose attack. Our code is available through the GitHub QR. Don't forget to check the Offensive AI Lab website for more interesting projects and collaborations. Thank you. I will now take questions from the audience.
Yeah, before you ask question, just name yourself, okay? So who is the first? Okay.
Thank you very much. That was a very interesting talk. I'm Sundar from UCL. And I was wondering, you made claims about how your attack strategy is more robust than the LSB hiding strategies and stuff. And I was wondering whether you did any experimental analysis on this?
Yes, we did. It is in the scope of the paper. We have a full section about this.
Okay.
In general, what we have found that we need actually very small magnitude of noise in order to completely remove the data embedded using the steganography methods. But for our method, that prevention mechanism completely unaffects the extraction.
Cool. Thank you very much.
Okay, any other questions?
Hey, I've seen the results for the celebrities and also for the first line for MNIST. Can you give a reason why in the Cypher 10 case, the results are, I would say, worse? So on the right side, the truck is barely visible. So what is the effect here?
Well, yes. Okay, we discussed this a little bit in our paper. Memorization with convolutional-based models is more difficult, thus the memorization quality is slightly reduced.
So it's because the first one has no convolutions and the last one also has no convolution.
First one is convolutions, and that's why the track is completely blurred.
Okay, I mean the first line is also with the MNIST fully connected is also with convolutions.
No, MNIST is fully connected.
Okay.
Okay, first one fully connected MNIST, second one CFAR with CNN, third one CFAR with Vision Transformer, last one Anceleb A with Vision Transformer as well.
Okay. Okay. Yeah.
Okay, any other questions? If not case, I think I have a question. So this transpose attack need to add extra training, like training goal in the training phase. So will the training be slower than the normal training?
Yes, a little bit, because in each training iteration we perform 2 gradient steps. But in general, it's not a lot slower because of optimization that we can make during the training process.
Okay, so do you have an estimation of how much slower?
We did not empirically estimate this, but I think that you're going for like, if this can be used to create a detection mechanism. That's right, okay. So I think that it's kind of impractical to perform detection this way because different models will have different training times. So in order to arrange a well-suited detector for this task, then you have to experiment a lot with all kinds of architectures and know their training times.
Yeah, so from your experience, it's in an acceptable range, right? So the training cost is in an acceptable range, right?
Yes, of course.
Okay, cool. So I'm looking forward to test your code.
Of course. It's available, and you're welcome to check it out.
Yeah, so the authors also mentioned their code is published in the last page, so if you're interested, do not forget to take picture. Okay, so thanks for the great talk, and let's give the speaker another warm welcome, and then let's welcome the next speaker, okay?